Good afternoon and welcome to the Computational Science Colloquium series. Today I have the pleasure to welcome Professor Xuanji, who is a research assistant professor at the SDSU, and he's going to talk about data science and solar panels. He's a material science guy.
Thank you. Hi, everyone. My name is Xuanji Yu. You can just call me by my last name, Yu. I just recently joined SCRRC at SDSU. I would like to talk about my research, which is applied data science in solar energy. I don't have a SDSU email address yet. Here is my previous email address. Please email me if you have any questions and interest.
Your work is pointed.
Yeah, it worked previously. Anyway, my computer. Okay, yeah. So the talk will be divided into 5 parts. Basically, I will give an introduction of the background, and then I will divide this talk into 4 parts based on the data type, including time series data, photovoltaic image data, text data, and climate geospatial data. A quick introduction of myself. So I got my PhD from Boston University. My major is material science and engineering, working on the reliability of polymer films for semiconductor industry. Then I work in Canadian solar panel manufacturer for 2 years, working on the performance and the reliability of solar panels. And then I serve as a postdoc at Case Western Reserve University. The reason I go back to academia is that during this working period of time, we designed lots of physics-based or semi-empirical based predictions by our customers and or other researchers. They're interested on the real-world data, so I joined as a postdoc to learn more about the data science and data-driven approach for the analysis. For today's talk, I will mostly talk about this part. For solar energy, one of the key parameter we really care about is how much energy produced over the lifetime of the solar panel. There's a parameter called LCOE, levelized cost of electricity. So basically, the equation is very simple, just the sum of the cost of the solar panel over lifetime divided by the electricity energy produced. So the lower, the better. As you can see here, the solar panel produced LCOE is decreasing. So this factor is affected not only by the performance of the solar panel itself, so basically initially how much power it will produce, but also on the reliability, meaning that for example, if we imagine a solar panel working for 100 years, so this LCOE will be very low and superior to other energy. So it's so basically we care about the initial power produced, which is the power at first, and then as you can see, the power will drop over time, impacted by the power degradation. Also, there are failures sometimes, and those are decided by not only the solar module technology, so different cell technology, different encapsulation, also environmental factor. For example, irradiance, temperature, humidity, hail will break your glass, solar, snow, wind will apply the load on the solar panel, flood, fire, etc. So those are some of the failure solar panels. So we want to avoid that. And if we can design like very reliable solar panels and high performance, then it will be superior to other energy source, basically. The tradition, this is the structure of a solar panel. Basically, it's kind of like a laminated photo. Inside is photovoltaic cells. It will absorb light, produce electricity, and it's laminated with polymer and glass. So like a laminated photo to protect the cell. Basically, I'm interested in accurately predict the performance and reliability of the solar panel. The traditional research is we're using standard conditional testing, basically like fixed solar irradiance and at the same temperature, and measure the power panel will produce, and do the accelerated testing, which is high pressure, high humidity, high temperature, see when the panel will fail, and do some physical or semi-empirical based prediction. But in the real world, it's very complicated. I'm interested in learn what the field data will indicate, what material parameter would be best in field, and also the compatibility between different materials. Also, if there is a proactive operation and maintenance of the panel, it can prevent failure and etc. So yeah, data-driven approaches in solar energy. Second part of this talk is on solar energy time series data. Basically, it's power produced by solar panel. This is a time series data of 2-day data of a solar inverter. But as you can see here, in this image here, those are heat map of the time series data. Basically, we plot the time series data in 2D form. So the y-axis would be the time during a day. Y-axis is time during a day. X-axis is different days over like within several years. So as you can see, the heat map, warm area would be during the day, it will produce electricity, and the dark area is nighttime. So basically, so this would be a good time series data, but very often the data we got is something like this. So there are a lot of erroneous data, so means that it's wrong data, bad data. Also, there's outliers. For example, the solar panel power produced by solar panel will be affected by like fog. Also, like a cloud. If a cloud flies by, then you will affect your performance. Those bad data will impact the decomposition, time series decomposition, and forecast. So the traditional way to handle this problem is to use data filtering method to filter out bad data, but the result is often affected by how you filter the data. So it has bias and inconsistent. So yes.
But if I have solar panels that live by the coast and there is fog and all this stuff, even if you filter whatever, the performance that I have doesn't change.
Can you see that
my
again?
house.
So
what I'm getting in my house is not going to change if you filter the data from all the area.
Yeah. So yeah, but if we can somehow distinguish, okay, right now there's a power drop. If we can distinguish like data-driven approach, tell you whether it's because of like fog or cloud, or actually because of there's something wrong with your solar panel. Maybe we need proactive maintenance, meaning like cleaning the solar panel, or like something's wrong, right? They may cause fire and stuff. So one of the the motivation is to distinguish whether it's bad data because the sensor is wrong. Maybe they actually produce power, but they didn't record it, or it's like outlier because the cloud, etc. So research tasks including data imputation, so fix missingness and outlier, data decomposition. So because power is affected by seasonally by irradiance and temperature, etc. So if we can decompose it and get the trend, we can compare like how the performance loss over time, like even the brand, etc. And also for the accurate forecast, so we know what we'll produce in the future. It's very short period of time. So the country, first, I would like to talk about data imputation. There are several challenges. Firstly, there are multiple missing scenarios, including missing completely at random, or block missing, etc. So the severity, etc. So it's hard to capture the missingness and do the imputation by a single model. Secondly, is that often the power produced lacks ground truth, so nobody can really know like what should be the true data if a chunk of the data is missing, as you can see here, and it's affected by seasonality. So we want to. The idea is that how do we know if the data is like bad or not? If we can compare the data of this location of your solar panel, if you compare with the nearby solar panel performance. So if the nearby performance is good by your performance job, it means something is wrong with your panel. So if we can somehow utilize the spatial coherence, so modules located near each other, or if we can utilize the temporal coherence, meaning that we compare the current data stamp with near timestamps. Also, like a long period of time, if this date power compared to previous year, to decide whether this is good or not, and then do the imputation. The module architecture we use is a graph neural network autoencoder. So graph autoencoder consists of encoder and decoder. Basically, this is an example of autoencoder. So we have original input. We partially destroy the input, meaning that we add a 0 to it, and then encode the input data, and it will find the compressed low-dimensional representation of the input, and then use a decoder to reconstruct the input. So this is the idea of the autoencoder, and we can add the denoising architecture, make sure it's like robust against the noise. We use graph neural network to the architecture. Basically, you can think of each node of the graph representing a solar panel. And if the solar panel is very close by with each other, for example, as this graph shows, if like all at California, they should perform similar to each other. And versus like on the East Coast should be similar to each other. And we can adjust how we want to connect the solar panels or the nodes based on the distance. And then do data augmentation. Basically, we do some pre-imputation using the domain knowledge. So we have the if we have the solar irradiance data, we can fill in some predetermined values based on the domain knowledge, and then corrupt the data by removing chunks of data, turn them into 0, and change the neural network. So we also did compare with the state-of-art imputation methods, including like KNN, mice, linear interpolation, etc. So as you can see, the spatial temporal graph autoencoder performs well, better compared to other traditional imputation methods. This is a imputation. So the graph gray is the ground truth. The red indicates the spatial temporal graph autoencoder reconstructed data, and blue is missing data points. As you can see here, if there's a 40% missing completely at random, we can still reconstruct the data. And if it's a block missing, we remove a block, like the blue area data, it can still reconstruct based on the nearby. So gathering information from the nearby solar panel, you can still reconstruct. Like here is a lot of power. Here, the power is impacted by the clouds, very close to the ground truth. And this package is we published the package on PyPy. It's called PV-PLR FDGNN. Please feel free to use it. So here are the raw data. We also did some transfer learning. So use a chain model to see if it can fix the missingness of another data set. So as you can see, there are big chunk of missingness, and here is a round data because it doesn't produce any electricity somehow or zero. And after the imputation, you can reconstruct the data. So another topic is data decomposition. Basically, we want to find the trend of the data so we can compare performance. For example, California versus a place like Ohio, for example. California has more sunlight. You cannot just compare the power itself. You have to remove the seasonality and the impact by the environment, and then compare the trend, basically. I will be skipped. The idea is that the temporal variance is very similar if they are close to each other, and we can get a trend of the time series data. And to improve the neural network, one idea is to add a tension mechanism into the neural network because the performance of the panel not only depend on the location, if your two guys are similar to each other, also depend on the brand of the solar panel and the climate type, etc. So this is some future work. Also the same mechanism can be used for time series energy data forecast, and this can be combined with energy management of a building, for example, with solar. So if we can do accurate prediction, we can know how many power it will produce, for example, within next day or within next 5 days. And like this, if there's like a weather hazard, etc., you can store more electricity. Yes, something like that. Yeah, there's some future work. So to give you an idea of the systems, time series data like we have is 100,000 systems across the US. So it's like a non-trivial, it's big data problem. So neural network can do a good job. Secondly is photovoltaic image data. A lot of imaging technology is used for solar reliability study, including drones, which is very popular. So basically, we'll fly over a PV power plant and see if there's some hot spot, something is really hot, which is not good for the panel, something's wrong. Also, there's thing called electrical luminescent image. Basically, you bias the panel, it can shine light out. This is a solar panel after many years of like field operation, and you can see the degradation over time. So the power produced will decrease. Another thing is like a UV ultraviolet fluorescent image. So basically, you can detect a crack within the solar panel. So there are many research tasks based on the image data set, including image segmentation. So because the field image, for example, taken by drones or arcs, we have to segment the image into a PV module or a solar panel or a single solar cell. Also correct the distortion, etc., perspective distortion, etc. Another task is image classification. So different deviation mode, whether there's some cracking in the cell or there's corrosion, etc. So we know whether this is significant or not. So this talk I would like to focus on image regression. So basically, we want to just take a picture, and for example, by a drone or something, it can quickly tell you the performance of the solar panel, whether it's good or not. So here is the data set description. The inputs would be the electrical luminescent image at different aging step. So as you can see, there are more dark spots showing after a long time aging. So we divide it into the data set into training, validation, and test set. Also rotate the image different degrees to do data augmentation, and then train it with neural networks. The model architecture we use is CNN, recurrent neural network RNN, and the CNN plus RNN. So the basic idea is that CNN is very popular, utilized in image classification. It can extract the feature of the image. For example, we use CNN to extract the important feature that is related to the degradation, and use RNN, which can utilize the temporal information, how the image degrades over time, and predict the power performance. There are many hyperparameters used, changed for the neural network. Also, the neural network design is different with different drop-off layer, dense layer, max pooling grid, regularization, batch normalization or not, etc. Because there are a lot of model variants, we use the distributed computing using Slurm to manage resource, so can train many neural networks at the same time. The conclusion is that we find that CNN and RNN model is very similar for different kind of image inputs, meaning that we use raw image versus like processed image. For example, enhance the ratio of the image. So the neural network result performance is very similar for different kind of inputs. So the idea is that the neural network can very well predict the performance regardless of the pre-processing of the image, because CNN can extract the features that are important. Another takeaway is that for the RNN model architecture, so recurrent neural network, it can achieve the best performance even using the raw image. The reason is that recurrent neural network utilizes temporal information. So how the image change over time, so it can do the most accurate electricity performance prediction. Yeah, this is like a summary. Next, I would like to talk about text data, mostly metadata. If you are a data analyst or doing data science, mostly often you find that a lot of time you spend on is actually cleaning the data. Once you have very clean data, it's easy to do the neural network training. Especially right now, we have PyTorch, we have Keras, etc. This is also a big problem in science, especially, for example, I'm doing material science. Most often we use synonyms. For example, temperature is a very important parameter. Some people write it temperature, some people write T, some people write a temp. So if we want to utilize all those data, it would be very difficult to change one by one. Also, people have different ways of saving data. There's like write down on notebooks or saving Excel, PowerPoint, etc. And the last problem is that the data lacks structure. I will use the structure of solar panel again, use the example. So because I work on this field, I know the structure of the solar panel. It would be nice if we save the data nicely, so you can just look at the structure of the data. You know that solar panel have those components. The motivation is that for the better documentation and the management of metadata, and remove the challenge in sharing data, and also like a next step for AI task. So the research data should be not more than just a paper or like a project report in company. It should be for other people or for future use. The way to do it, there are many efforts doing that. The mostly renowned one is called a verification of data sets. Basically, it's the FAIR principle, which is makes data findable, accessible, interoperable, and reusable. So like the and there are some further application. For example, if everything is well organized, structured, the data, there might be possibility for the graph, not to build a knowledge graph. Here the example of Google knowledge graph. So the node would be entity of like people, etc. And edge would be the relationship. So by building a knowledge graph, we can do some basic query. For example, it would be great. I can just type in. So what's the best solar panel technology that is suitable for California? It will give me some recommendation, something like that. So this is an example of Google. So find the right thing, and it also can search further information. So what we did is like some preliminary work. So basically, we want to verify the unstructured real data into structured verified data. So we go there using index by the JSON-LD, which is JavaScript objective notation for linked data. So it's structured, preferred by Google, and it has context that will link to ontology. So if people are new to this field, they can click the link and find the information. And also key that defined in taxonomy. So we use the same name, or it has a list of similar names that meaning indicate the same thing. So it would be something like this. This is an example of the apple pie recipe. This is a JSON-LD file. It contains all the information, like a context, what that mean, and the relationship, and also the data information, author, etc. We developed a file material, R and a Python package. It can, this is an example, we can input unstructured data, including data frame or CSV, and then verify it and produce the output will be the verified JSON-LD. So this is the example of non-fair data CSV of a solar panel. So for example, it has the power at a standard test condition of about 445 watts. And the output would be something like this. So as you can see, it has the value of the data, it has the unit, the description, and also the structure. So solar panel has all those kind of like properties. So easy for other people to use. Also, if someone is new to solar, they can understand somehow like by looking at the JSON-LD file. Yeah, this is a effort. A lot of people working on this, including like 10 computer scientist students and 30 material science scientists. Because different we need a lot of people to build the JSON-LD template to manage the big project. We use a Jira board, which if you work in data science, you might be familiar for the project management. And there's also a website, so people can see the data, for example, JSON-LD structure and the documentation of different material, yeah, etc. Yeah, this is like a summary. Turn unstructured real data into structured verified data. Yeah, this is a Python package. Yeah, as the future work might be like if we use natural language processing. So somehow if we feed the system enough data, they will somehow recognize, okay, temperature and the temp, maybe they are similar, like Google and Siri. Yeah. Last part of the report is climate and geospatial data. So I will briefly introduce the climate geospatial data in solar energy and its big data challenge, also application, etc. The goal is that we need a comprehensive climate or geospatial data set for solar. Because it's very important for the performance estimation. If you want to install a solar panel, you want to you need to have a very accurate estimation of how much power it will produce, because it's affected by irradiance, also affected by elevation. For example, if you are near a very high mountain, especially here in San Diego, there's probably long time shading, so you can't have any sunlight. Also soiling, if somewhere like desert, there will a lot of dust accumulated on the solar panel, and the snow, cloud, etc. Temperature would also affect the performance. So again, geospatial and climate data is very important. Also, it will affect the degradation, meaning that if the same solar panel installed at here versus Florida, probably Florida, it has larger degradation because it's humid and hot. Also, some risk factors, including hail. If you live in Texas, there's a historically more chance of receiving large hail, which will break the glass. Also, salty water, snow, etc. Yeah, so it's important. Those data are important for the forecast, maintenance, and energy management, especially facing the extreme weather conditions. So why I say this is like the biggest data problem, because GIS, geospatial information system, I believe is a very old and well-established research area, major. But right now, the global satellite image can be as accurate as 30 meters. As you can see, this is a global digital elevation map of New York City. Actually, I got this from Reddit. As you can see, it's very accurate, and it can show lots of small details. The resolution is 30 meters. So there will be a big data problem, because this is only store one information, elevation. If there are more information, including irradiance, temperature, cloud, etc., there will be a big challenge. Also, this change of the elevation don't change that much over time, but the other climate data change a lot over time, climate change, etc. So also there's a challenge because there are a lot of, actually, if you search online, there are a lot of data source. They have different temporal span, different temporal resolution, and different spatial resolution. So how can we assimilate those disparate different data sets? So if we want to use it, for example, I have very high resolution image. If I want to add other climate data, how can I produce such also very high resolution data sets? There are many ways to do the data interpolation and the data assimilation. Some of them are from geostatistics, mostly from, for example, from the petroleum industry, because they basically utilize the spatial continuity. So if we can find oil in this area, most likely there's an oil nearby. So something like that. So the closer you are to each other, the more coherence. Also, it's very important to estimate the uncertainty, of the prediction, etc. I will give you an example. We are working with a climate classification. This is a prediction of Copenhagen climate zones. It's a traditional climate classification based on temperature and precipitation used for farm and like grow crops, etc. So right now, the state of art can produce very high resolution Copenhagen image. So for solar, we want to add. So for people to utilize that, basically, if you want to, for example, use this climate data to do some classification task, it would be nice to know the Copenhagen climate zone of any location. So I write this Python package. It can tell you the Copenhagen zone information of any latitude, longitude, etc. So here is the example. Giving latitude, longitude, you can tell you, okay, here is at the ocean. If the other longitude, latitude, it can tell you what kind of climate zone it is. Furthermore, because irradiance is very important for solar, so I use a data interpolation to create a high resolution map, and I added the irradiance information to the Copenhagen climate. So you can see this is a traditional resolution, and then we have a high resolution. And in the future, it will be even higher. So this is like just the first steps. In the future, if we can also create a map, for example, for hail. As you can see, this is a hail hazard event map of the United States. Red dot means that there's a large hail event happens. For example, at Texas, lots of hail. California, no hail. So if we have more climate data, and we can have create more maps. Whether it's hail or degradation, and the snow and the wind load, etc., to do prediction. I will end this talk with some key takeaways. This talk, I briefly introduced some of the applied data science in solar energy. I guess the takeaway is that to achieve optimal results, it's very important to use model architectures and tools that can effectively utilize information with domain knowledge. So for solar energy time series data, the reason the spatial temporal autoencoder works really well is that the spatial temporal graph neural network can use the temporal coherence, also spatial coherence. Basically, automatically compare with the nearby site just to fix the data of your solar panel. And also the domain knowledge-based pre-imputation is important. probably cannot have any missing links to train a neural network. For solar image data, photovoltaic data, image data, the recurrent neural network performs best because it utilizes the temporal information. So the one solar panel degraded over time, you can most accurately predict the performance. For text data, it's very important to use a domain-based structured data for data management or for future knowledge graph. For the spatial geospatial data, it's important to use the tools that make sense. For example, geostatistics interpolation, like kriging. So use the spatial coherence nearby for the interpolation. Yeah, that's all. Any questions? Thank you. Yeah.
Is there a reason you didn't use the variational autoencoders?
Variational autoencoder. Yeah. So we couldn't find a way to encode the location information into the neural network. So basically, we use graph neural network with that. So we can easily use adjacency matrix to. So for example, those PV sites are close to each other, so they exchange information, but not the PV site at Massachusetts, for example. So
there are variational graph neural networks, though. So I thought
a graph, a variation
yeah.
graph. Okay,
yeah.
variational graph neural network. Yeah, so here the autoencoder we used we use basically we use a convolutional neural network. The reason is that we think if you look at the heat map of the time series data, it kind of like utilize the nearby information. For example, the today versus yesterday, they probably produce similar kind of like solar energy. So we use a conventional neural network, to capture that information. Yeah, that's maybe one thing like we can try. Also, right now there's a transformer, right? If we can somehow utilize, so it not only compare with the yesterday information, the day before yesterday, but also like 1 year before, right? That would be great. But it's yeah.
Yeah, and that was my next question. Is
Yep.
like, is there any way we could add modalities to it? Because there are like some cross attention architectures that could use those like different modalities to like account for some non-linearity. So yeah, I was just wondering like what modalities would you be willing to add to it?
Okay, sorry, I'm not a computer science major. I could explain the modality.
And like for example, like you got UV or like
yeah.
like data.
Exactly. So right now we only feed in the time series power data. So as you everybody know, very important data affecting solar is irradiance data. Yeah. We plan to add that as well. The challenge is that so power data is usually is very accurate. But the solar irradiance data, you need to install a device to actually capture the local irradiance. That is pretty difficult, also expensive. People just buy a solar panel, not install any sensor, right? Usually, except for large power sites. But for large PV power plant, they usually install several. So it's not actually the exact location for that panel. Yeah. And there are also many challenges, including like sensor drifting. So the sensor, you have to maintain calibrated, so it's kind of a mess. Yeah, but definitely for sure, somehow the network can tell you whether this is a sensor problem or actually it's something like that. It's very useful. Another possibility we are thinking is that adding the satellite image irradiance into that. Since satellite image is like covers the whole Earth, is very accessible. Yeah, something like that. Definitely for sure. Yeah, that's a great idea. Yeah, great comment. Thank you. Yeah. Yes.
What was the first Python package again?
Python package.
Or like, what was it called?
Yeah, we try to think some flashy name, like right, like we call it PVPRR SCGN. PV is for seller, PRR is performance loss rate analysis. Yeah, yeah. So actually, we got this idea from traffic forecast. So a lot of traffic forecasting use neural network. Since you may know that the traffic here is very heavily affected by nearby traffic. So if the traffic accident ahead, it will very impact your traffic. So yeah, please welcome. So any like a task that you need to utilize spatial temporal information, that might be yeah, works for you. Yeah. Yes.
You started with the motivation that you wanted to predict reliability of your photovoltaic system.
Yes. Yeah.
And you didn't quite quantify it, but I'm assuming it says, can I produce the minimum power required after a certain amount of time?
Yes. Yeah.
So now you've gone and you've done several things. One is you can predict the time series variation of the power loss over time.
Power loss
And
over time. Yes.
you try to correlate it to geographic conditions, climate conditions.
Yes.
I didn't see it connect back and say, I can, for a given location, for a given brand, tell me what's the reliability.
Yeah. That would be the
All this is good, but where's the proof of the pudding?
So it's not achieved yet. That will be the ultimate goal.
So what is missing then?
What is missing? So we find that neural networks is very good, do a very good job for the short-term forecasting. So for example, if I want to predict the performance in next 5 days or like a week, that will be very accurate. But for long-term, maybe we need like more information. For example, longer time series data, and also maybe more advanced model architecture, like transformer and stuff. So also the industry is changing quickly. For example, like kind of like your iPhone, it had a different generation. So once they use a new material, then the data we have is like either outdoor like for 2 years, which is very too short to do the prediction, or it's mostly indoor data. So like it's kind of difficult, but this would be a very good framework if we keep doing this. And when the technology hits a bottleneck, it will be useful for prediction. Another thing I would like to emphasize is that yeah, there's an ultimate goal, but those things currently is still very useful. For example, the autoencoder can detect whether the data is bad or not. So, for example, automatically tell you if your power is significantly lower than the powers nearby. So you have to do active maintenance. That's why we work with a solar inverter factory. So they are interested in this kind of technology. So proactive maintenance, something like that. Yeah. Yes.
What kind of maintenance like stops solar panel degradation, and like do people who just buy it for their homes like know about it?
Yeah, very good question. So one I will give you 2 examples. Firstly is like how do I say elegantly, like for example, a bird poop. So if there's a bird fly by, it will cause some shading for the solar panel. It's not because if you imagine the bird poop is very small, right? But because it's shade part of the cell, so that part would not produce electricity. Basically, it's like kind of a resistance there, so it will produce heat. So it's not for the solar panel. And that would not only the performance will loss, also impact your long-term performance. So that's why you can clean it. The other example I would like to give is macro crack. So especially here at San Diego, 1 month ago, there's a hurricane, right? So when hurricane comes, it will make the solar panel vibrate. So if you imagine the solar cell is silicon, right? If you vibrate it, it will have micro cracks. So those cracks will also cause problems in the future. So something like that. So if or maybe a baseball. So it's like a golf ball. Yeah. Like the other side, people don't know why it should produce a lot of power, but not. The only reason that is near a golf ball. Yeah, court. So
like, if you know that a hurricane's like coming,
yeah,
can you just like cover the solar panel? Like, do people?
usually not. Yeah.
Would that help?
Then this is another research subject. So there are some, especially United States, there are some like very high-end tracking companies. Basically, they design the racking of the solar panel, basically the support structure. So there are ways to mitigate that and stuff. Yeah, it's another. Yeah, I don't know how to decrease the vibration. Yeah, but I know for hail, particular, if there's a hail event, there are some solar panels, they have a tracker. See, it's not fixed structure. It will rotate like kind of like a sunflower. So facing towards the sun all the time, something like that. So if there's a hail event, it will like slow. So it will become vertical. So the hail less likely to break the glass. Yeah. So a lot of times, because I also did a lot of like field surveying. Basically, I go to power plant to see if they are good or not. A lot of time they are not that well maintained. Yeah, so United States like it's very good economically. So a lot of those old PV solar sites, they are used as economical resource. So for people, if you have extra money, it's a kind of investment. You want to buy this or not. So those are kind of tools. This could be useful to show like, okay, if I do the auto encoder to fix data and I do the performance loss decomposition, I can tell you, okay, this site actually works pretty good or not. So those kind of data, yes.
Did you also apply this research to concentrated solar plants?
Concentrated solar panel.
No, plant. It's where they have a bunch of mirrors they heat up a liquid.
Yeah. For that, it's not as well. I mostly work on photovoltaics. So photo produce voltaic the current. Right. So yeah, that's also one of the research area. But I believe because that it has to occupy a lot of land. Also, it will have very high intensity light. So usually it's in desert and stuff. But for solar panel, you can install anywhere. So yeah, it's kind of like a lithium-ion battery right now because it's cheaper, it works better, so it's dominant, kind of like that. For solar panel compared to that, it's more dominant for solar panel. But maybe in the future they have some new technology somehow. Yeah. That's yeah. Yes.
What percentage would you say of the data was missing? And then is there a threshold where like the neural network wouldn't be reliable?
Very good question. So it depends on the data set. This example, this actually is from a Florida public school or something. So because they don't have the incentive to maintain that, so the data is really bad, as you can see. In some cases, it's pretty good. Some cases, it's all wrong data, something like that. So it depends case by case. So in terms of missingness, currently the neural network can fix up to 40% missing complete at random and 6 hours block missing. Yeah. Yeah, this kind of also depends on the missingness in different sites, for example. So if you imagine, okay, I have a site that is a lot of data is missing, but the nearby site, they have a lot of data, they can still fix that data in that site. Yeah. Yes.
Two comments.
Yep.
Technical term for cooking is biofouling.
Thank you.
Sounds more
technical, yeah. More serious researcher. Yeah.
The second comment is, this is relied completely on data.
Yeah.
Right,
Yeah.
and there's with physics. If you know your system, your materials, your risk of impact and cycling, you can have a physics-based prediction which you can enhance with data. Whereas if there's no physics enhancement and you're trying to do this, one.
Yeah, actually, that's the ultimate goal, I would say. So as you can see here in my presentation, I actually did some physical-based prediction. So this actually is a power loss over time of a solar panel in places like Brazil. This is the reliability, i.e. the how many panel you have to replace over time. So I will call it failed panel. Yeah. Yeah, that was definitely the ultimate goal. If the data-driven result is compatible, or like combine them together, actually this is very helpful. So when I do the continuous auto-encoder, because for some data they are so bad, we have to do some pre-imputation. So do the pre-imputation for the data augmentation, I use a physical-based method. So to fix the data first, if the big chunk are missing, because otherwise they cannot change in your network. You can fill it in at 0, but it will affect the performance. Yeah.
A limited way of using the physics.
It would be great. Yeah. Yeah. And very often, so it's kind of like the Toyota, the car. So different manufacturers, the manufacturing process like impact a lot. So in solar area is in particular, I would say like sometimes the lab result cannot reflect the factual, the commercial one. So it's yeah. So in factories we do the standard test, also the accelerated aging test. So accelerated stressor, high temperature, high humidity, see whether it can last longer than previous generation. So we can have some idea. So it's definitely much better, but how much? That's the question. Yeah, it would be great to improve, but yeah, for some data scientists, they will say that this result is biased, right? Some people like it, some people don't like it. So, yeah.
And then the speaker when you want.